welcome guys. Okay, so in this video, I want to talk about examples of Cantor's diagonal argument. Okay, so there are many examples of this Cantor's diagonal argument. So this is very interesting. So the first examples, I think everyone, if you study analysis or something, the first things that people want to talk is the real number is uncountable. Okay, so the proof is that let's only consider the 0, 1 open interval. Okay, then the idea is that one can suppose that 0, 1 is countable. So that means one can label the A1, A2, A3 in a 0, 1, right? And we know that any number in a 0, 1 can be written as the infinite string. So let's say A1 can be 0, let's say D1, D2, D3, and all Di are from 0, 1, or 2 up to 9. Okay. A2 is 0 dot D. Okay, I don't have enough variable. Let's say this is C. Let's say C1, C2, C3. A3 is 0.3, E1, E2, E3. Okay. Or basically, if I can write 0, 1, A1, 1, A1, 2, A1, 3. Okay, and then 0 point A2, 1, A2, 2, A2, 3, and then 0 point E. Okay, A3, 1, A3, 2, A3, 3, and keep going. Okay, and all this Aij belongs to 0, 1, 2 to 9. Okay, and so the subtlety is there. The subtlety is that this Aij there may be different string representation for A1. So for example, if A1 is 0.1, then you can have 0.100000, or A1 is equal to 0.099999. So the problem is that we may have different representation. Okay, so the idea is that let's eliminate these type of representation. So that means I forbid any string with infinite consecutive lines. So I don't allow any kind of this thing 0.9999 happen, right? So that means every string can have is enough. It can only be least type. Okay, and then let's say R is point 0 and 1 in open interval is countable, so we get it, right? So the proof is very easy. Let's suppose you already label it. Then I can construct a number. Let's call it A. It's 0.0. The first condition I choose is different from D1. So if D1 is anything 0, I can choose D1 maybe 1. Okay, whatever. So I can choose as D. Let's choose that I choose it to be B1. So the B1 is not the same as A11. Okay, and then I choose B2, and the B2 is not the same as A22. Okay, the B3 is not the same as A33. Okay, so idea is that you see, since A1 is different from B1, right? And we already omit this situation, so that B1, so A is not different from A1, and the same reason B2 is different from A22. So A is different from A2. A is different from A3, right? So by construction, A is not the same as any AI. So it's not the same as AI. So that means this is contradiction, right? Because we guarantee that we already label all the number showing 0, 1 open interval. Okay. Hence 0, 1 is already uncountable, so reals is uncountable. Okay. So the second example, I want to show that 0, 1 infinite is uncountable. Okay, so this means that let sigma to be a 0, 1. Okay, so 0 sigma is just a set with two elements, and the 0, 1 infinity means a set of all infinite length binary strings. So for example, let's say 0, 1 infinity is countable, so that means we can write A1 as a 0, 0, 0, 0, 0, 0. Okay, so A2 may be 0, 1, 0, 1. A3 may be 1, 0, 1, 0. and A4 can be 1, 1, 1, 1, 1 or something. Okay, so to go infinite. Okay, let's say this is uncountable, right? And the same technique I think everyone knows. I can construct the A, right? If the first thing is 0, I put 1 here. If this guy is 0, 1 I put here. If this guy is 1, I put here. If this is 1, I will put here. Okay, so I choose. So I choose A. The ith position of A, I define to be negation, right? If 0, 1, 1, 0, negation of the AI at ith position. So by construction, A will not fall into this, right? But we already know A definitely be this guy, right? So 0, 1, infinity is uncountable. Okay. So the immediate consequence is that the set of all computable languages are countable if you know about computer science. So lemma is very easy. Let's say sigma is some finite set, and the sigma star is a set of finite length string composed with sigma. So let's say sigma is 0, 1, right? And the sigma star is all finite bit string. So maybe 0, 0, 0, 1, 0, 0, 0, 1. Okay, so this is exactly what? Exactly countable. Okay. So any programming language is combined with some sigma. Everybody's agree with that, right? Because your programming languages only have finite symbols. So the set of all sigma star or sigma, okay, I should say sigma is is countable, right? So that means sigma star is countable. So we know that any programming language is combined with some sigma. So that means all the programming language output is countable, right? But all the differential problem is a set of R. Okay, so the set of all computable languages are countable. Okay, and so this why this is true, right? Because you can view that any real numbers, right, can contains any. So any differential problem is the same as the real numbers, right? Because you can have the infinite type of inputs and you just corresponding with 0, 1, or 0. So this is maybe false. This is maybe true or something like this. Okay. Okay, so the number, for example, is also is important called more than reals. Okay, so this is the easy function, the easy way to construct a number which is construct set which cardinality is greater than real. So let's consider A is a set, basically real function from 0, 1 close interval to R. So this is real. Okay, I claim the cardinality of A is larger than the cardinality of reals. Okay, the reason is also simple. Let's say cardinality A is the same as real. So let's say this is 0, 1, right? So I want to count any function from here to here, from 0 to defined to be 0 to 1, and I collect all of these cardinalities larger than cardinality of reals. And the reason is that so what is the reason? The reason is that suppose. So let's say suppose the real. So by definition, we know that we can consider constant function, right? So we have a constant function from R mapped to A. So that means the cardinality of A is greater or equal to R, right? Because if you take any real number, I can just create a constant function, right? And then they're all different. Okay. So all we need to show is that there's no surjective map from there's no surjective map from R to A. So there's no surjective map from R to A. Okay, so the idea is that suppose there is, right? There is a surjective from map from R to A. So that means for any A, right? For any A, you can. So let's suppose that you use R to label A, right? So that means any function. So you can construct, you can have a, right? So that means any function A. So any function in A corresponding to some alpha, right? There's alpha belongs to R such that F is labeled can be viewed as a F alpha. So that's F is just let's say this map is G. So F is just G alpha. F for some alpha is real. Okay. right? But there's a trouble, right? Because if all these functions are labeled by R, right, then for each real point, right, then I can construct another function which is definitely not the same as all of it. How to construct, right? If for each alpha, right, then I will get some g alpha, right? So g alpha is a function, g of alpha. Then I can construct a function, let's say k, right? I choose k alpha is different from g alpha, right? I can always choose that. So suppose you have a function which is here, then I choose another function which is different, which at alpha is different from u, right? So I can choose a function which k alpha equals to is not the same as g alpha for all alpha. Is it correct? Okay, yeah. So I mean for each alpha, right? For each alpha in real numbers, there is a function. There's a fixed function called f. Right? So the f is a function called g of alpha, right? But at that alpha point, I choose that's I should say. So I should say for that alpha point, I choose alpha alpha. So I pick up I create a function. Let's say k. That function at the alpha is different from the g alpha alpha, right? So this is not correct. Okay, so at least results, right? Because for that k function, right, at each alpha point is not is designed to be different from g alpha alpha. So it's proof that k do not fall into any alpha. So k cannot be labeled by any alpha. Cannot be labeled by any alpha. Right? So it proved that the cardinality of A is larger than cardinality of reals. And this can be used as a continuous version of Cantor's diagonalization argument. Okay, so this is the 4 simple application of Cantor's diagonalization argument. And I will see you guys in the next videos. Thanks.